Thanks everyone for joining, and thanks Sarah for the kind invitation. My name is Mattia Bulla. I work at Stockholm University. Before that, I did my PhD at Queen's University in Belfast, and then I moved to Stockholm about 4 years ago. I was a first postdoc in the Type 1a supernova cosmology group for 3 years, and then I moved to Nordita next door, where I was a Nordita fellow, and since last week I'm actually at the Department of Astronomy at Stockholm University, thanks to a starting grant from the Swedish Research Council. And so today I'm going to talk about some recent efforts in trying to model kilonovae from binary neutron star and black hole neutron star mergers. But before starting, I should say I'm really lucky and thankful to the wonderful collaborators that I have in the past couple of years, including people in Stockholm, but also people like Lina, an undergraduate students from Paris-Saclay, Shreya in Caltech, a graduate student at Caltech, and then Sarah, Michael, and team that are also part of the grant collaboration. And so before starting, digging into kilonova, I thought I had to include one slide at least on GW17 So as you all know, I guess this was the first gravitational wave signal with a confirmed electromagnetic counterpart. And so that goes back to August 2017, when a gravitational wave signal consistent with a binary neutron-star merger was detected by LIGO, and follow a couple of seconds later by a gamma ray detection from Fermi and integral, and that of course triggered a lot of excitement around the globe, and pretty much anyone who had a telescope pointed into the localization area suggested by LIGO, Virgo, and the gamma ray observatories. And about 11 hours later, a new transit was found in this galaxy that was later confirmed to be the electromagnetic counterpart for this event. And so why there was so much excitement? What were the predictions in terms of the electromagnetic transits for these events? And this is a nice cartoon from a review article by Stefano Scienzi, where the different components that are expected are highlighted here and are connected to the actual transit that you're expecting to see. And so first of all, there is this jet that is launched during the merger that is powering these gamma ray bursts, and perhaps also this cocoon created from the interaction of the jet with the surrounding material. But I won't talk much about this component. Then there's also this GRB afterglow that is created when the jet actually plunged into the interstellar medium, and then you power this afterglow at longer wavelengths. But today I'm going to focus about this component, the so-called kilonova, that, as I said, was identified for this event. And you can see here, like discovery, this transit was pretty much blue, but then got redder very rapidly. And so the agreement within the community was that you need to have at least two components, the so-called blue kilonova and red kilonova. But I'll get back to these in a few slides. But first of all, what is actually a kilonova? So this is using the words from Brian Metzger from his paper in 2010. Kilonovae are electromagnetic counterparts of compact object mergers powered by the radioactive decay of R-process nuclei. And so let's imagine we have a seed nucleus with some number of protons and neutrons, perhaps similar number, but in a very highly neutronized environment. So you have a lot of free neutrons around. So what happens is that you get the neutron captures very rapidly, so via this so-called rapid process or R process that basically doesn't allow you to decay back. And so you build up this very heavy and highly neutronized nuclei through this R process. And the R process is also responsible for the creation of about half of the nuclei heavier than iron, as you can see here in this periodic table. In this respect, one key parameter is the so-called electron fraction. So this is the number of protons basically divided by the number of nucleons, protons plus neutrons. In normal matter, this number should be, it's close to 0.5 or exactly 0.5. So the number of protons and is similar or equal to the number of neutrons. But in this case, so what happens is that in the R process, if the environment is sufficiently neutronized, let's say Y is smaller than 0.5, but larger than 0.25, then you can create elements up to barium here. But you can actually produce these very heavy elements. But if somehow you manage to get Y is even smaller than 0.25, this kind of threshold value, then you can produce these very heavy elements, including this whole lanthanides here and part of the actinides here. And in the rest of my talk, I will refer to ejecta having this very low Y as lanthanide rich, and those with Y larger than 0.25 as lanthanide free, as done in the literature. So now we have these very highly neutralized nuclei, but these are very much unstable. And so they very quickly decay back. And so you have this radioactive decay that produce gamma ray photons. And gamma ray photons, at least part of them, are trapped because the environment is still very dense. And so they basically, at least part of them, thermalize within this ejected material and basically set the temperature, which just for reference is around 5,000 to 10,000 Kelvin, depending on the different parameters at 1 day after the merger. And so you basically thermalize, and then the subsequent thermal emission at longer wavelengths is what we actually call kilonovae emission. So this is an emission at longer wavelengths, ultraviolet, optical, infrared, that then propagates throughout the ejected material and then eventually escape to reach the observer. And so last year, I spent some time and developed this 3D Monte Carlo radiative transfer code called POSSIS to model kilonovae. And so I just want to highlight the key ingredients here. So the first one is you basically create Monte Carlo photons that are assigned some properties, most notably frequency that you get from the actual temperature in the ejecta, and energy that you can get from the nuclear heating rays that basically tell you how much energy is produced through the radioactive decay of these R process elements as a function of time, is shown here. But also you need to account for some thermalization efficiency. So basically the fact that not all the energy that is coming from radioactive decay actually end up thermalizing the ejecta. But then once you assign those properties, you can start the actual propagation. And here the key parameter is the so-called, the opacity. So basically this kappa value here that together with the density basically set the optical depth of radiation in its propagation, and basically the probability of interacting with matter. And the main source of opacity in kilonovae is bound opacity. So these are like line absorption and re-emission from these lines from our process elements. And here the main takeaway is that the opacity kappa is very much different depending on what composition you have in the ejecta. So if the ejecta are lanthanide rich, then especially in the optical here, so the bound opacity, line opacity is much higher, so orders of magnitude higher than the one in the lanthanide free component. And this basically tells you that kappa will be larger in these environments, so tau will be also larger, and the probability of interacting will be higher. So you basically, the diffusion through this lantern reach ejecta, diffusion timescale will be longer. So it will take longer for radiation to escape through those regions. And then finally, when you get the radiation to escape, you can use these Monte Carlo photons to create observables, synthetic observables like spectra, so flux as a function of wavelength, and then it's also as a function of time. And from those, you can get lighters in whatever filter you want, and also polarization. So my code also includes a polarization treatment that allows you to calculate basically the polarization signal from kilonovae as well. And so in the past couple of years, I've been developing a few kilonovae grids. So here I show just the most recent ones. I won't go into all the details, but the main takeaway here is that these are far from being spherically symmetric, and you basically have different regions with different ejective material with different compositions. And so what I show here in red are like lanthanide rich, blue is lanthanide free, and perhaps this green that is emitted post merger is perhaps intermediate YEs. So here I show a binary neutron star grid, and here is one for a black hole neutron star. I should say that part of this grid were also done by Lina, this undergrad student from Paris during her time in Stockholm last year. And one other thing is that, so of course the geometry is a bit simplified, but guided by numerical relativity and hydrodynamic simulations. But we basically varied different parameters like the ejecta masses of the different components, the half opening angle here of this lantern reach component, and the viewing angle most notably. And the same here where, however, we fixed this half opening angle phi. And so you can run a large grid of models, which in this, for the BNS case, is roughly 1,500 models, while around 900 models for the black hole neutron star. And one thing is that, I mean, this is all public. So all the grids that are produced through POSSIS are public. So you can go to this GitHub page and grab the models you prefer, and then use it as you like. So I do encourage you to do so if you want to use these models. Before I actually go to the applications, I would just want to have one slide on important key parameter, which is this viewing angle dependence. So as you might have noticed, these are, as I said, not spherically symmetric. And so you naturally have a viewing angle dependence based on the fact that the composition and then opacity in different components is different. And so roughly speaking, the two main observables are in terms of the absolute magnitude, so how bright the kilonovae is, and the color. And so here I'm showing prediction for just two viewing angles, one looking face on, looking the system face on, so along the jet axis, and one in 90 degree away, so in the merge plane. And you can see that if you look at towards from the jet axis, the kilonovae is brighter compared to 90 degree away, again, because radiation can escape more easily in these blue lanthanide-free regions. In terms of the colors, so here I'm plotting like an optical filter like G minus an infrared filter K. And generally speaking, you see that kilonovae indeed go from blue colors to redder colors. So they get redder very rapidly, actually. But you can see that there is also this viewing angle dependence where observer in the merger plane will see redder colors compared to those along the jet axis. Okay, so I'll try now to briefly summarize some of the works that have been done in the past couple of years using prediction from POSSIS. I won't have time to go into details, but you can ask me later on, check out the publications actually. So the first one is a paper that was actually led by a graduate student here in Stockholm, Anna, um, where she basically took one of my grids and look at the detectability of kilonovae depending on the limited magnitude and the filter combination. And so here I'm showing the viewing angle as a function of distance. And this is the 90% probability of detecting kilonovae if you only use GNR filters and you go at 21st magnitude deep. And then you, of course, you see that GW17 or 17 was an extremely lucky event. So it was a view very close to pole, where when the kilonova is brighter, and also was very nearby. And so, of course, this 21st magnitude was enough. But if you look at this other BNS from O3, it was too far away, so there was no chance of detecting these with this magnitude limit. But then, if you include I, the first takeaway message is that you indeed can go a bit more farther away. Basically, you can detect kilonovae farther away, and also perhaps kilonovae larger inclination, so farther away from the pole. And so the first message is you have to go red, but also you need to go deep, as you might imagine. So we looked at how these changes would go into 22nd and 23rd mag, and you can see that you can easily, with 23rd mag, easily reach these 200 megaparsec or distances where you would expect to see most of the gravitational wave events. And perhaps you can also get these very large inclination for closer events. The other thing we looked at was how these changes, if you manage to get a first detection within the first day. So in this one, there's no constraint on the first detection. And so if you have a first detection within the first day, this is even better. So I can maybe flash through these two slides, and you can see that you can go even farther away. But the takeaway message is go red, go deep, be quick, which I guess, at least qualitatively speaking, was probably something people expected. But here we were trying to basically quantify these statements. And finally, I should have said this is with best fit model to 17/17. So it's basically the probability of detecting another kilonova exactly the same as 17/17 kilonova. But we also, of course, looked at the whole grid, and here it's just a plot showing how these probability changes if you depending on the model parameters like this phi angle, like I mentioned before, and the total ejecta mass. And so if the ejecta mass is larger and phi is smaller, then you expect to get brighter kilonovae. And so the chances are even higher for a reference distance of 200 megaparsec and 22nd mag. Then I thought I had some slides on the efforts to detect kilonovae in L3. And so there are many papers that came out of this, both from the Grove collaboration I'm part of, but also from other, including Gramma and other like Engrave. So I won't have time to go through all of them, but I decided to just show one example from this paper led by Shreya and Michael that was published last year in Nature Astronomy, where basically what I want to show is basically how even getting non-detection, so all this non-detection we got from O3 is actually powerful to constrain the parameter space of models. And so this paper focuses on three events, three candidates for black hole neutron stars. This is now confirmed to be a real event, as you all know, I guess. And so we first look at like this event here, and these are ZTF observations in GNR. And these are basically open symbols are each pointing within a given night, and the field symbols are the median upper limits. And you can see here that we were a bit unlucky, and so the upper limits were a bit too shallow. And so basically all the models in my grid are fainter than these, and so you basically can't rule out anything. Even if the kilonova was there and you managed to image that particular field of view, the kilonova was too faint. But then we did the same with this other event. And again, probably a bit too shallow, but you can start perhaps ruling out some models, as shown here in light blue, but only if the actual kilonova was at the closer end of the distance posterior from LIGO. So this event was found, was suggested to be, the gravitational wave signal was suggested to come from about 340 megaparsec plus minus whatever, 80 megaparsec. But for this other event, instead, the DECAM observations were taken in radar filters also, I and Z band, and sufficiently deep, let's say 22nd Mach, to actually rule out a good fraction of models. And so for this specific event, we could actually rule out part of the parameter space of the models. And so all the panels here show the ejecta mass in this post-merger disk wind component as a function of the ejecta mass in the dynamical component here. And each panel is a different viewing angle range. So here we are close to pole, here, let's say here in the merger plane or close to, and here for intermediate viewing angles. And you can see that basically for a polar viewing angle, or let's see, an observer that is within, let's say, 26 degree from the jet axis, then you can basically rule out any kilonova with, I guess, ejecta mass larger than 0.01, which is the smaller value in the grid. For equatorial viewing angle, though, the kilonova will be faint enough to be basically fainter than the upper limits. And here you can perhaps, for this viewing angle range, constrain the ejecta masses to be perhaps 0.04, 0.05, depending on the actual distance. In the paper, we also played this game and look at how these constraints for these other two events, how the constraints change if you assume you were lucky enough to go as deep as the deepest pointing within the night. And so you can see that here you start probing. If you manage to go to 22nd Mach, you start ruling out models, and this is basically the same plot. But still, the takeaway message, I guess, is the same one from the previous paper. You have to go deep. So 22nd is probably not enough to either rule out or preferably like actually detect kilonova in the future. And also going redder, like getting this I band and Z band, is actually more constraining than just GNR. So I thought I also have a few slides on application in terms of measuring the Hubble constant. And so the Hubble constant H0, which is basically a measurement of the local expansion rate of our universe. So the universe is expanding, the velocity, basically each galaxy is receding from us with a velocity proportional to its distance, and this rate, the actual rate is exactly h0. And you might have heard that there is this growing tension between measurement of h0 from the late universe, so most notably type 1a supernovae, that get a value of about 73, and compared to there is a tension between this measurement and early time measurements from CMB, for instance. And this is a 4 to 6 sigma tension, depending on which probe you use. but it could be due to systematics, unknown systematics in either of the two approaches. But there's also the possibility that this is new physics. And so this is I receive a lot of attention in the past years. And having an independent approach to arbitrate this tension could be really useful. And so already in the 80s, gravitational waves were suggested to be used that could be used as standard sirens, where you basically get the distance directly from the gravitational wave signal and the redshift perhaps from the identification of an electromagnetic counterpart, and perhaps also from the host galaxy. And so this is a relatively model independent approach, as long as you believe GR. But the drawback here is that there is this known degeneracy between in the gravitational wave signal between the distance and the inclination of the system. So basically an edge-on system closing would produce a gravitational wave signal that is equal to one face-on but farther away. And so these basically result in a degeneracy between H0 and inclination, as was shown in for GW17 or A17 here. And then when you actually get the posterior on H0, this is not first of all is consistent with the two measurements from Planck here and Shoes, type 1a supernovae, but actually arbitrate the tension. And here is the, I think, either the mean, I think it's a maximum posteriori value they got from this paper. And so having an independent way to constrain the inclination would be really useful. And this is where the kilonovae could say something. And so this is a paper that was led by Suhail Dhawan at Stockholm University, where we basically took one of my grids for BNS and basically find the best fit to the data of GW17 or A17 and constrain the inclination. So here you can see in red our posterior on the inclination of the system. So where this would be an observer on the jet axis, so looking at the system face on. So GW17 or 17, as you also know and other studies have shown, was not exactly on the jet axis, but slightly offset. And so using this constraint, this contour, black contour, that is exactly that H0 inclination degeneracy I showed before, that contour actually shrinks of about 24% in terms of the maximum a posteriori region. And then here you can see how the actual error bars, uncertainties on H0 decreases using kilonovae. A similar approach was taken by Michael, again using both my grid, but also grid from Dankeisen, where in addition to GW17 or 17, he also used these 4 historical short GRBs where a kilonova component was suggested to be present. And here again, you can see, I mean, with a slightly different approach, but still the idea is the same, how you can reduce the uncertainties on H0. And finally, just a couple of slides on this other idea that Michael came out with of actually getting H0 with using kilonovae alone, so without gravitational wave, where you basically get the not only the redshift, but also the distance from the actual kilonova, where you basically, the whole idea is you use models to get the absolute magnitude in some band, let's say the K band infrared. You go and measure what is the apparent magnitude, and then you get the distance right away. And so these are plot from the paper. It's a busy plot. I don't want you to get everything here, but the main idea is that you can. Each point here is a model from Dankeisen grid, And what's plotted is the absolute magnitude in K band as a function of a color and a shape parameter, basically how fast the kilonova decay from peak to 7 days later. And then you can get the absolute magnitude in K band as a function of these two parameters. And this is done, this function is actually found through some Gaussian process regression-based interpolation. Or alternatively, you can get that absolute brightness directly from the actual model parameters. So there are these two different approaches, and what you get is shown is summarized in this plot. So you should focus on this orange line, which is the H0 posterior using only gravitational wave, and the blue lines are using kilonova only from the grid from Dankhausen, and the two different approaches, and the green one is using my grid in one of the two approaches. And you can see again, you get consistent results with the gravitational wave analysis, slightly, I guess, within a factor of perhaps 2 uncertainty. So it's not as competitive, but the whole idea here is that in the future, we might hopefully get some kilonovae serendipitously without gravitational waves. So one can play the game and get H0 also with kilonova. And then just one slide on this new framework that is basically a nuclear physics multi-messenger Bayesian framework. And this is an effort led by Team D3, where as essentially the whole idea is to put all the pieces together and start with equation of states from nuclear theory computations of chiral effective field theory here, and then put those together with pulsars measurements, gravitational wave measurements, electromagnetic measurements, and get constraints on H0, again, as shown here, but also on the equation of state, and here shown as the radius of a 1.4 solar mass neutron star. I won't go into the details, but this is, I think, a very promising framework. It was also used recently in a paper that was recently actually accepted, led by Ingo Thiers, where this framework was used to constrain the nature of GW190814. And then one final slide before I wrap this up about other application of POSSIS that I won't have time to go into details, but one is, as I mentioned, the polarization signal. So we had a couple of papers, one for BNS and one for more recent on black hole neutron star, where we look at the polarization signal that is expected from these mergers. Because, so basically you get polarization signal from electron scattering, which is shown here as this horizontal line. And you can see that actually for the blue lanthanide-free component, at this wavelength, electron scattering could be dominant or at least comparable to line opacity. And so you can get some polarization. And so in these two papers, we make some prediction that if you are quick enough, so if you get spectropolarimetry, most likely for very nearby kilonovae in the future, then you can get some polarization that, first of all, can help you to get constraint on the inclination as the polarization changes as a function of the inclination, but also be a smoking gun for this lanthanide-free component, which is the only region where you expect polarization to come from. And finally, one recent paper led by a graduate student here in Stockholm, Lorenzo, where we look at how the interaction of the jet with the ejecta actually affect the observables, and the takeaway message is that this should make kilonovae brighter and bluer, as shown in this plot here. So you basically, the first couple of days, first day especially, you can get an increase in magnitude of about 1 or 1.5 magnitude, and this is stronger in bluer bands. Okay, so this is actually my final slide. Sarah sent me 3 questions, and so I'll try to answer these 3 questions. So first of all, what brings multi-messenger astronomy for your research? And I guess I hope I convinced you during my talk that multi-messenger astronomy actually gives observational data, not only detection, but also non-detection, that are really, really useful to test and constrain the models, and actually also to push myself to develop more sophisticated model grids. And in terms of the challenges, I think the most important challenge that I see is to try and quantify the model uncertainties in these radiative transfer codes, and most notably the lack of a complete atomic data set. So the fact that we basically lack a complete line list for all these heavy elements. And so what the impact of this is in terms of the observable, I think is still unknown or at least uncertain. And finally, what are the long-term impact of multi-messenger astronomy? I think this is probably pretty clear from all the studies that came out since 2017. I think it's pretty clear that multi-messenger astronomy will shed light on fundamental questions in physics and astrophysics, like some of those that I list here, like equation of states, origin of heavy elements, expansion rate of our universe. And I really think that putting joining efforts with different, astronomers, but physicists, and develop this kind of multi-messenger frameworks is really the way to go to nail down these questions. So I'll stop here, and I'm happy to take any question.